Good day, people. Welcome to One-on-One Maths Private Tutors. Today we are looking at simple harmonic motion in Cambridge and Zimsec A-level physics. These two syllabi, even in O-level, they are very similar. Okay, so simple harmonic motion is the topic we are looking at. Why do we study simple harmonic motion? Simple harmonic motion is very useful in design and construction of structures such as buildings and bridges. Case in mind is the Tacoma Bridge. If you go look it up on YouTube, you'll find that the Tacoma Bridge fell because of simple harmonic motion. The frequency of the bridge was equal to the frequency of the wind that was blowing. So it created a resonant frequency, which amplified the frequency of the bridge, and it began to oscillate and it collapsed. So it is a very important topic to study, especially if you are preparing to go into engineering, civil, construction, mechanical engineering. We'll be working on these things a lot. So at A level, we study it and it's in the syllabus. This is the chapter 17 of the Cambridge syllabus. What do we need to know? We need to know equations like this. Okay, these equations have to be known for simple harmonic motion as well as energy. And understand the terms that are being used, such as the velocity, the displacement, amplitude, energy, angular frequency, things like that. All right. So we have to understand oscillations. At One-on-One Maths Private Tutors will provide you with books and A-level textbooks that you can use, electronic textbooks that will send you through on WhatsApp or email, so that you get familiar with these things, and we conduct live lessons on Zoom or prepared videos for each section of the topic so that you can understand. And then we provide you real life past exam questions like the one we are about to attempt. So this past week, we have been working on simple harmonic motion problems after completing the chapter. All right, let's look at this question. A U-tube contains liquid as shown in Fig 3.1. So this is 3.1. This is the U-tube. The U-tube, okay? The total length of the column of liquid in the tube is L. So this is the length from there all the way to there. All right, the column of liquid is displaced so that the change in height of the liquid in each arm of the U-tube is X. So we can see it in Fig 3.2. So they move this column down and this one goes up. All right. The liquid in the U-tube then oscillates with simple harmonic motions such that the acceleration A of the column is given by the expression A is equal to minus 2G over Lx. Okay, this can be measured. Let's see what they gave. Calculate the period of the oscillation of the liquid of the liquid column for a column length 19 centimeters. All right, so the first thing we might want to do when we are dealing with in physics, change the quantities into standard quantities. We don't use centimeters. So 19 centimeters is equal to 0.19 meters. Okay. So we are given this expression. But what do we know? Let's look at the syllabus. The equation we are accustomed to is this one. A is equal to minus omega squared x. So our acceleration is equal to minus omega squared x. So what do we say about this? Acceleration is the same, x is there, so the only difference is the negative is also there. So the only difference is here and there. Okay, here and there. So we can substitute omega squared is equal to 2g over L. So the first thing is to give this equation that we know and compare it with the proposition that is there. All right, and see what we can substitute. The only difference there is 2g over L and omega squared. So these should be the same. These quantities should be the same. All right. But what do we want? We want the period. We know angular frequency, which is our omega, is equal to 2 pi f. All right. And frequency is equal to 1 over t. So we can say omega is equal to 2 pi over t. Cross multiplying there, we get t is equal to, or we can just substitute omega for 2 pi over t. So now we have 2 pi over t squared is equal to 2g over L. Let's make t the subject of the formula. So we can square root both sides. So from there, we can go on to square rooting both sides. 2 pi over t is equal to the root of 2g over L. All right. Cross multiply there, 2 pi 2 pi over the root of 2g over L is equal to t. So know how to manipulate your equations to change subject of the formula. So t is equal to 2 pi over 2, g is 9.81 over L we have been given, it's 19 centimeters, which is 0.19 meters. 0.19, which will give us our t ultimately as 0.62 seconds. All right. So our information is given to two significant figures. Yeah, we can leave it at two significant figures. So 0.62 seconds is the period. Right. Okay, let's go to question B. The variation of time of the displacement x is shown in fig 3.3. This is the displacement with time. You can see the amplitude is being lost as we move with time. All right. The period the period of the oscillation of the liquid column of mass is 0.18 is T. So let's look at it. One oscillation, T. Another oscillation, 2T. Another oscillation, 3T. So that is the oscillation. And you can see the period is the same. All right. Period is not changing. All right. Let's look at it. The oscillations are damped. Okay. What is damping? The loss of amplitude as time as oscillations go on. Suggest one cause of damping. Okay. I would suggest friction between the walls and the liquid. Walls of the U2 and liquid. Because as the liquid oscillates, it's rubbing against the walls of the U-tube. All right. Calculate the loss in total energy of the oscillations during the first 2.5 periods of the oscillation. Okay. So what do we know about energy of the oscillations? From our syllabus, we have this formula. E is equal to half mass omega squared x naught squared. Right. So x naught is the maximum displacement, which is the amplitude. So we can use this. You see, potential energy, the interplay between potential energy and kinetic energy of the system. When the displacement is maximum at x naught or at minus x naught, we have our potential energy being the maximum, which is also coincidentally the total energy of the system. So at maximum amplitude, which is here, we have the total energy of the system. Also here, let's look at 2.5 oscillations. This is one oscillation, this is 2 oscillations, this is 3 oscillations. So halfway between is 2.5 oscillations, which is here. Right. What is the corresponding x naught value of the amplitude? Because that is the one we should use to calculate the energy. This is -1, so this should be minus 0.9. All right. So we have 2 and minus 0.9. So energy is determined, total energy of the system is determined by the amplitude, because we have E is equal to half m omega squared x naught, which is our amplitude squared. All right, let's look at our values. Initial, which is E1. For E1, what do we have? X naught is equal to 2 look, we are using centimeters. We have to convert this to meters. So we divide by 100 or multiply by 10 to the minus 2. Okay. Since the period is the same, the frequency is the same. All right. So omega is equal to 2 pi. 2G over L. Where do we get that? We have been given this. We compared omega squared to 2G over L. So omega squared is equal to 2G over L, which is 2 times 9.81 over the length 0.19 meters. Okay. What else do we need? Mass is 18 grams. We have to convert this into kgs. So it's 18 over 1000, which is the same as 18 times 10 to the minus 3. All right. For this is E1. Now for this E2. E2 x naught is equal to 0.9 times 10 to the power minus 2, because this is centimeters, we have to convert it to meters. Okay. Omega squared, the period is the same throughout, so it's the same. So it's 2 times 9.81. So omega squared is 2 times 9.81 over 0.19. M, the mass is 18 times 10 to the power minus 3, which is the same thing. So now how do we calculate this? E1 is equal to half M omega squared x naught squared, which is half times 18 times 10 to the power minus 3 for the mass, times omega squared 2 times 9.81 over 2 times 9.81 over 0.19. Okay, x naught times 2 times 10 to the minus 2 squared. 2 times 10 to the minus 2 squared. This should give us, let's go to our calculator. Half times 18 exponent minus 3 times 2 times 9.81 over 0.19 times the bracket of 2 exponent minus 2 was bracket squared. This should give us 3.71 times 10 to the minus 4 joules. All right. Now let's go on to calculate E2, which is the energy here. So E1 is the energy there. So that's why we're using 2 centimeters. So for the energy here, we use minus 0.19. All right. So E2 is equal to half m omega squared x naught squared, which is half times the mass is the same, 18 times 10 to the power minus 3 times omega squared is 2 times 9.81 over 0.19, the same as there, times what we only change is the amplitude, 0.9 times 10 to the minus 2 squared. What would that give us? Going to our calculator, half times 18 exponent minus 3 times 2 times 9.81 over 0.19. Times bracket of 0.9 exponent minus 2 close bracket squared. Okay, this is 7.53 exponent minus 5. Okay. Now, change in energy is equal to E1 minus E2, which is 3.71 times 10 to the power 4 minus 7.53 times 10 times 10 to the power minus 5. What would that give us? 3.71 exponent, no, minus the exponent minus 4 minus, and okay, so we'll get 2.96 times 10 to the power minus 4 joules. So that should be change in energy. All right, so a lot of things to consider, a lot of working to be done, but that is A level. And this question is 3 marks. Okay, so it spells how much work you have to do. That is the work you have to do. Conversion into standard units, and then working out using the given formulas in the syllabus. So that's all about energy. All right, thank you, people. Remember, we are engaging in our daily lessons at one-on-one maths private tutors, maths and science tutors, maths, physics, chemistry, biology, computer science, IT. We have a team of expert teachers who will take you through these courses, and our study is exam-centered. After completing every chapter, we look at the real exam questions. and discover and tame the tricks that they use. Almost all the time is the same tricks. So you'll see after we have covered 5 or 6 past papers or past questions that the tricks are generic. This can be done. All right. Thank you, people. Check out our website, our Facebook page, and our YouTube channel. We have videos there where we work out problems from past exam papers. All right. Thank you.